In this podcast, we're going to be looking at some properties and proofs with parallelograms. And then if we have some time, we'll continue on with solving with trig ratios. All right, so here's our first proof, and we're given parallelogram ABCD. And our goal is to prove that AB is congruent to CD and AD is congruent to CB. So we're actually proving one of the properties of a parallelogram. So because we're proving a property of a parallelogram, we can't just say it's a parallelogram and say, okay, because it's a parallelogram, the opposite sides are congruent. We actually have to prove that. So we're proving that this property of parallelograms is true. All right, so but that doesn't mean we can't use other properties of parallelograms. Okay? We're only proving that the opposite sides are congruent. So we can use the fact that this is a parallelogram to state that the opposite sides are parallel. Okay? And so we started off with that ABCD is a parallelogram, and that is our given piece of information. Because it's a parallelogram, we can state that the opposite sides are parallel. And you want to mark this. So when you're given something or you are you've shown something to be true, mark it on your diagram. So we want to mark that AB is parallel to CD and AD is parallel to CB. Okay, so our opposite sides there are parallel. Okay, so you can never use what you're trying to prove as part of your proof. That always has to be your last statement. So you can see what we're trying to prove is our last statement. All right, so but because we have stated that our opposite sides are parallel, because we have parallel lines, we know some things about the angles. Right? So one of the things we know about these angles is we know that angle ABD, and I'm going to switch colors here, ABD, which is this angle right here, is congruent to angle CDB. We also know that angle ADB, so ADB, this angle here, is congruent with angle CBD. Right, so why do we know that those pairs of angles are congruent? Well, if we have parallel lines cut by a transversal, we know that the alternate interior angles have to be congruent, and those are alternate interior angles. They're on opposite sides of that transversal. So the reason for both the next two steps is the same. Alternate interior angles formed by parallel lines are congruent. Okay? And make sure you add that step to your proof. Since it's the same reason, I'm just going to use the marks there to say that we've got the exact same reason. Right? So we have same reason for the next step as well, that the alternate interior angles formed by parallel lines are congruent. You could also shorten that and say alternate interior angles theorem. That theorem states that if we've got parallel lines, the alternate interior angles are congruent. All right, so now if you've noticed with the parallelograms, there's a common theme here. And one of those common themes is if we can get some triangles congruent, we can get some other things congruent as well. And here we're actually very close to getting a triangle congruent. Matter of fact, the only thing, we need one more piece of information. And that piece of information is that BD is congruent to BD. And how do we know that segment is congruent to itself? Well, the reflexive property says that you are congruent to yourself. Segments and angles are equal to themselves. Okay, so reflexive property is the reason that that segment is congruent to itself. Now that we have those pieces of information marked, we do know the triangles are congruent. And which postulate are we using? Well, we're using we've got an angle, a side between, and another angle. So that is angle, side, angle. So this is angle, side, angle, triangle congruence postulate. And yes, you will use these triangle congruence postulates, so you need to remember them from last semester. Now that we know the triangles are congruent, we know all of the corresponding parts are congruent. And so now we can say any corresponding part in this triangle is congruent to the corresponding part in the other triangle, because corresponding parts, and I'm going to actually write it out so you remember it, corresponding parts of congruent triangles are congruent. Or you can abbreviate that, CPCTC. If the triangles are congruent, all the corresponding parts are congruent. And remember, you cannot say that until you have stated the triangles are congruent. Right in the step above it, right there, we stated the triangles are congruent. Now we know the corresponding parts are congruent. Okay? A very common theme is to prove triangles congruent, because if we can prove triangles congruent, we have other things congruent as well. All of those parts of those triangles are congruent. All right, so when we've done several proofs like this, so I hope this one made lots of sense for you. All right, so now let's take a look at one more proof. Okay, so here I filled in some of the reasons. We'll fill in the other ones on your notes. We're given that ABCD is a parallelogram. We want to prove the diagonals AC and BD bisect each other. So we're trying to prove that, so we cannot state that because it's a parallelogram, and it's a property of parallelograms that the diagonals bisect each other. That's how we know. Can't state that. Okay? So we're trying to prove it, we have to show it's true another way. We can't just use the fact that it's a parallelogram. However, we can use anything else about a parallelogram. So we have ABCD as a parallelogram. That one is a given. And angle BAE. And I actually didn't write this proof. I borrowed this proof because I was looking for a fill-in for us to go through. And actually, I think there should be a statement that's said between 1 and 2. But let's go over step 2. So BAE is congruent to angle DCE, and angle ABE is congruent to angle, that's just CDE, a letter there is peeking out, to angle CDE. So the statement that I feel should be said before we make that statement there is the fact that our sides are parallel. So yes, it's a parallelogram, but really, I'm going to put a little asterisk here. It should have been said that CD is parallel to AB, and AD is parallel to CB. And of course, the reason opposite sides in a parallelogram are parallel. Are parallel. So that really should have been said there first. And of course, the reason that those angles are congruent, they are alternate interior angles formed by parallel lines. So we definitely should say formed by parallel lines if we don't add that extra step in there. Okay. AB is congruent to CD. That is a property of parallelograms. Opposite sides of parallelogram are congruent. And now we know that triangle ABE is congruent to triangle CDE. Again, this is angle side angle. Triangle congruence postulate. And now that we know that the triangles are congruent, all their corresponding parts are congruent. And so that means that AE, that is a side in one of our triangles there, is congruent to CE, the corresponding part. We can tell by the angles, that's the corresponding part. And BE is congruent to DE. And actually, I should put 2 here and 3 here, so they don't look like the other ones that already marked those sides. All right, so we know those sides are congruent. Those are sides in our triangles, and we've already proven our triangles congruent. So if the triangles are congruent, then all of the corresponding parts are congruent. Right, I'll abbreviate this time. CPCTCT. Corresponding parts of congruent triangles are congruent. Right? So you should be thinking that when we're proving triangles congruent, and then immediately after that we state something's congruent. Okay? We're using our corresponding parts of congruent triangles. The fact that the triangles are congruent, the corresponding parts are congruent. And because those segments are congruent, we know that E has to be the midpoint of AC, and E is the midpoint of DB. Definition of midpoint is listed there. Another way we could write that, and it's more of the explanation of what the definition of midpoint is, and that is, and I kind of like this one better, midpoint divides the segment in half. So you can just state that this is that's the definition of a midpoint. That's what a midpoint does. It divides in half. I kind of like just using the definition. So midpoint divides segment in half. That's what it does. It's right in the middle. Okay? So because our segment is divided in half, E is the midpoint. And because we've got segments intersecting each other in the midpoint, they are bisecting one another. So definition of segment bisector, the segment bisector intersects the segment at the midpoint. Right, so here we have proven that our diagonals bisect one another. If we didn't want to use both of the alternate interior angles, we could have used our vertical angles. Right, and had we used these vertical angles instead, we would have used a different proof, a different triangle congruence postulate. So, for instance, if I'm just going to erase this so you can see. If we had used the vertical angles instead of the alternate interior angles, let's say maybe we used one pair of alternate interior angles, and we said, let's use the vertical angles. Kind of like those vertical angles. Now we would have had a different triangle congruence postulate. This one would have been angle, angle, side. So you can solve a proof more than one way. Okay. In this case, we used the alternate interior angles. We could have used one alternate interior angle and the vertical angle. We know the vertical angles are congruent as well. Okay, so just a couple different ways to solve this proof. All right, and so let me know if you have any questions on these parallelogram proofs, proving some of those theorems about a parallelogram are true. You do need to know the properties of the parallelograms. Okay? There are the 5 ways to prove that a figure, a quadrilateral, is a parallelogram. In our last 2 proofs, we proved 2 of them. We proved that the diagonals bisect one another, and we also proved that the opposite sides are congruent. That was the one we proved. So it's getting a little sore here. All right, so make sure they're in your notes. Make sure you review those. Okay. Also, make sure you review the properties of each of the parallelograms. Okay, so I also have listed the parallelogram ones one more time. And then the rhombus, the rectangle, and the square. Make sure you review those. Okay, so each figure has some unique characteristics. All of these figures have the properties of the parallelogram. They are all parallelograms. So these parallelogram properties are going to apply to every one of these figures. But the rhombus, rectangle, and square have their own properties as well. And actually it has all the properties of the parallelogram right in those boxes there. So the rhombus has some special properties because all its sides are congruent. Because the sides are congruent, we end up with perpendicular diagonals and the diagonals that bisect each of the opposite angles. Because the rectangle has If its angle's congruent, it has special properties. It makes the diagonals congruent. And then the square has all of the properties of the parallelogram, the rectangle, and the rhombus. So make sure you review those. I won't go over all of them. They're right in your notes. All right, let's look at solving some trig problems. I think we can do that one on this tape, and then I'll finish up the rest of the review on another podcast. All right, so here we are solving using trig ratios. And remember, when we're working with trig ratios, we need two pieces of information. We either need an angle and a side or two sides. All right, so here we have an angle and a side. And we should also remember our ratios, what they are. Okay? Remember, sine uses the opposite and the hypotenuse. Cosine uses, and I really should put, we got to take the sine and the cosine of something. So I should really put the angle in there. So I'll just put in an A for angle. Is the opposite over hypotenuse. Cosine of the angle is the adjacent over the hypotenuse. And then tangent of the angle is the opposite over the adjacent. And whether you're opposite or adjacent depends on the angle point of view. Of course, the hypotenuse is always opposite the right angle. Okay. Here above we have the trig ratios that go with the problem there. So it's a measure of the angle is 65 degrees, and those are the trig ratios from the table. You can use those. You can use the table, or you can use a calculator, because the calculator has those ratios as well. Okay? I think for the sake of the podcast, I'll use, since they're up there, I'll just use those ratios, and then if I have a problem that doesn't have the ratios up there, I'll use the calculator. And you'll be able to see either way, because I'll use the calculator on the computer. All right, so angle of elevation, and when we see that, we know that the angle looks up. Of course, it's already marked in the figure. So angle of elevation is at the bottom looking up. Okay. So that angle of elevation is 65 degrees. We have the side adjacent to that angle is 22 feet. And we're looking for the side that is opposite. That is the opposite side. So which of our trig ratios uses opposite and adjacent? That would be tangent. So when solving these, don't do guesswork, solve it out, okay? And all you got to do is set up your ratio, right? So I'll just work it right here. So tangent 65 equals our opposite, which is h, over the adjacent, which is 22. You need to isolate your variable, so we'll multiply both sides by 22. So we have 22 tangent 65 equals h over 22 times 22. Those cancel, and now we have our variable isolated. 22 tangent 65 equals h. And if we're using the table, whether it's from the benchmark or we use the table, we use the table I gave you, you can replace that tangent 65 with the ratio that goes with it. You can also just plug tangent 65 into the calculator, make sure you're in degrees, and it will take care of that as well. It has that ratio, but to more decimal places. All right, so now we have 22 times 2.1445 equals h. Okay? And I will bring up the calculator. Just have to go over to the side here. All right, so then if I just multiply 22, oops, and I don't know, I see a screen recording thing, so it's blocking my calculator. There we go. I don't know if you see that, but I do. So we have 22 times 2.1445. My shadow's blocking as well. All right, so it's 47.179. These have been rounded, so choose the value that's the closest. Now, if yours is way different, then you've maybe made an error, your calculator's in the wrong setting, etc. It should be, if we rounded it to the nearest whole number or the nearest decimal, tens place, we should see our answer here. So we do see that 47.179 is just has been rounded to the nearest whole number. Okay, so now we found the answer to this problem. Okay, so that's all there really is to our trig ratios, right? We set up the ratio, we isolate our variable, and then we either use the calculator to get the value, the ratio for the trig angle there, the tangent of the angle, or the sine or the cosine of the angle, or you use the values from the table. Either is fine. All right, let's do another problem. All right, so we want to find the height of the door shown at right if the measure of angle CAB is 16 degrees. So this would be 16. And CA is 13 feet. So we're looking for the height of the door. We're looking for right there, X. Okay? So we know, opposite the right angle there, we know the hypotenuse. We're looking for the side adjacent. So this one is the hypotenuse. This side here is the adjacent one. And by the way, these are all in your notes. So make sure you're solving them along with me. So you practice it and you've got some examples. All right, so which one of our trig ratios uses hypotenuse and adjacent? Well, that would be cosine. All right, so we have cosine, and that's 16 equals the adjacent side, which is x or whatever variable you like, over the hypotenuse, which is 13. You want to isolate your variable, so we'll multiply both sides by 13. So we have 13 cosine 16 equals x. If we want to use the value from the table, we can just plug that in for cosine 16. So it would be 13 times 0.9613. That's equal to x. And I'm just going to get the calculator back out again. And we'll calculate that out. All right, so that's 13 times 0.9613. So 12.4969, very, very close to 12.5. There we go. So right there, our answer is 12.5. Okay. Okay, so yeah, but if you set these up correctly, they're really not too hard at all. All right, so we have a 50-foot ladder is placed 35 feet away from a wall. To the nearest foot, approximately how high does the ladder reach? Okay. Well, this problem here, we've got two sides of a triangle, a right triangle, and if you have two sides of a right triangle, don't use your trig ratios. Instead, you're going to use Pythagorean theorem because you don't have an angle measure. So if you have two sides of the triangle, use Pythagorean theorem. Okay? So just make sure you set it up right. Okay? And so the 50 here is our hypotenuse, and the 35 is a leg. So we have 35 squared plus, and we're looking for the height, okay, that's also a leg, plus h squared is equal to 50 squared. 35 squared, I do not know off the top of my head. I'm just going to grab a calculator and try and do this with one hand. So that's 1,225. So 1,225 plus h squared equals 2,500. Subtract the 1,225 from both sides. So we have h squared is 12, oh my gosh, I'm Must be tired today. Can't even subtract. You can see, if you look up at the corner there, 12:75, so I was about to write down what time it is. So I don't know, maybe it doesn't record that time there. I think it does though. So you can see it's really late. And so it says to approximate how high it goes up. So if it says approximate, you can get a decimal equivalent. And it might not be bad for us to review the exact answer. So the exact answer, if this simplifies, we would just divide, well, it's definitely divisible by 5, and that goes in 2, 5, and 5. That's divisible by 5. So that would be 51. 51 is not a prime number. It's divisible by 3, and it goes in 17 times. So 3 and 17 are prime numbers. So 1 5 comes out, 1 5 goes away. So the exact answer would be 5 square roots of 51, which is approximately, let's see, approximately 35.71 feet. So if it says approximate, you can get a decimal equivalent. Otherwise, we want exact answers. And so for missing, if you got two sides of the right triangle, just use Pythagorean theorem. Don't use a trig ratio. All right, so one leg of a right triangle is 12 feet. What's the length of the other leg if the hypotenuse is 20 feet? All right, this is, again, we've got two legs. So this is Pythagorean theorem. Now this one does not say you can approximate, so we should have an exact answer here. All right, so this is a leg. This is the hypotenuse. So, and we're looking for the other leg, so we have 12 squared plus h squared, whatever variable you like, h, x. Maybe I shouldn't use h because it sounds like hypotenuse. So I'll just use x squared equals 20 squared. So this is 144 plus x squared equals 400. Subtract 144 from both sides. So you have x squared is equal to 256. That is a perfect square. And 16 is the square root of 256. So that's our answer. So we have an exact answer here because it's a perfect square. So this is a Pythagorean triple. Okay, so 16. I'm going to do one more problem before I end this podcast. And we want to know the length of the diagonal if the height is 20 feet. This one, so the height would be 20 here. And this is a rectangle. We know because we see the right angle. And I could have said this is a rectangle. So I'm telling you this is a rectangle. So the opposite sides are congruent. So we can put the 20 either space. If you're going to use the 20 here, then this angle here, where I put an X, is not 70 degrees. It's not very well drawn to scale, but it would be 20 degrees, right? 90 minus 70 would give us 20. However, I'm going to use the other side. Okay? So I'm not going to use that one. I'll use this one instead. So we're opposite. Actually, I should go the other way because it's from the angle. So this side here is the opposite side. We're looking for the diagonal. The diagonal is opposite the right angle, so this is the hypotenuse. So who uses opposite and hypotenuse? That would be sine. So sine 70 equals 20 over x. Multiply both sides by x, so we have x sine 70 equals 20 over x times x. Those cancel. X sine 70 equals 20. And then divide both sides by sine 70 to isolate your variable. So x is 20 divided by sine 70. And now we would use the calculator. So it's a little tricky using the calculator on the computer. It's kind of backwards, but I'll use it. All right, so I have 20 divided by, I'm going to have to use parentheses, and I have to do the 70 first. So 70 sine, oops, and then close my parentheses. Did I hit it? Okay, yeah, it looks like I did. All right, so we get 21.284 feet. So I'm going to write that down. So x is 21 point, I think it was 284, right? So notice that's not a lot different than our leg. And that's because so I obviously didn't draw the angles to scale. I probably should have maybe moved the 70, make it look a little bit more like it was drawn to scale. But 70 degrees is a pretty large angle in a right triangle. It's almost as large as the right angle. So the side opposite that 70-degree angle is going to be the largest side. And because there's not a whole lot of difference between the 90 degrees and the 20 degrees, our hypotenuse here is only a little bit larger than that side opposite the 70-degree angle. All right, so this was the last problem I have on trig ratio. So as you see sometimes we'll use Pythagorean theorem when we have two sides of a right triangle, and then sometimes we'll use our trig ratios. In the next podcast, we'll look at circles. All right, but I'm going to end this one now, and have a great evening.